seminar. It is my pleasure to introduce Mario Ullrich from Johann Kepler University Linz, who will talk to us today about random matrices and L2 approximation using function values. Mario, please.
Okay, so thank you very much. Yeah, I think I think that's quite nicely related to the talks that are usually here, although the topic sounds a bit I don't know, more general or something, because usually it's more about specific point constructions. But here in my talk, it's more about how powerful are point evaluations in general, right? So I will formalize all this a little bit and go through these details here. To say what I'm doing afterwards, I will do an introduction with the result, present an example. I have this thing here. So some examples. I will then show what this has to do with least squares algorithms, and to show you what all this has to do with matrices, especially random matrices, I will go through the proof here. So Ryan, again, how much time do I have? Do we have just to be...
You have
50 minutes.
Okay, so I hope to manage to do it in 50 minutes. Otherwise, I have to skip small parts, so I have some options there. Okay. So what is the general motivation? If you are doing numerical analysis, which I would say is my main topic of research, then you always have, say, 3 pieces that need to be specified before you start with whatever you are doing, right? So you have some given function or functions, actually, that you want to recover or approximate, or at least some property of it. You need to specify what you mean by an error, because I'm not talking about exact computations here. That's more a discrete mathematics topic. And the third thing is, you know that f is only known through some pieces of information, right? And what I've already said, so some things I say again yesterday, and then yesterday, that's strange, somehow to give the same talk twice. So please excuse me if I'm a bit confused at some points. So what the main problem here is, I think, that the first parts get quite a lot of attention in the literature, but the last part actually not. So what information do you have allowed of your function that you want to approximate, and especially how important is this choice? Okay, so to be a bit more precise, assume an arbitrary measure space, take the space of all square integrable functions on it, and consider a subset or subspace of L2 of functions. Okay? And this subset should be a separable metric space. So sometimes it's easier to talk about examples or to think about examples. You think on whatever example you want to. Okay? So E could be the cube or the whole space or even the natural numbers, right? So you think about sequences, basically, and equipped with an arbitrary measure mu. You could also take the sphere, because this is something that is often used in this workshop, whatever, right? F, now the unit ball of a separable normed space. Just take it as an example. General result will be separable spaces. Yeah, we need some assumptions clearly. So F should be embedded into L2, which means that the identity is injective and compact. So that's a classical assumption here. And what we want to do is we want to compute, in a theoretical sense, an L2 approximation of a function with a finite number of information, preferably small, clearly. And the reasons are several of them. The most important are probably we don't know f, and we just can take some measurements, take real-world situations in physics or whatever. And the second point is we know f completely. Think of an image or something that you stored on your computer, and we want to compress it because of some computing issues, right? So that's I think the 2 major tasks that you want to do in numerics. And for both, actually, this is a very important question. So what information is allowed for these processes? What is the information of f I can use, right? And in addition, and again, how important is this choice? So I note that this f as an element of f is seen as kind of an a priori knowledge of your f. That's something you don't need to measure, you know it in advance. So if you make a picture of stars, you know that's most likely only black with white dots, right? This is something you should take into account. This has nothing to do with any measurement. It's just the modeling of your problem. Okay, so what is information? And the most natural and also general class you can consider is you take informations given by an arbitrary linear functional. So you have your element f and you compute L of f and get some real number, and that's one information. Okay. But in general, if you're doing numerics or whatever, then you don't have access to arbitrary linear functionals. Instead, you have an admissible information class. It's called lambda and the following. But this could contain certain expectations, or so it contains functionals, right? So it contains expectation operators, or it could be the coefficients of some given basis, or, which is the main topic of this talk at least, is function values. I will also comment on other information in the last section if I have time for that. Function values is also a natural class. You can compute f of x for every x in the domain. Okay. What we want to do then is we want to use this information and build it together to an approximation. Okay? And here also, that's a restriction, that's a real restriction. I'm only considering linear algorithms in most of the talk. Okay. So I have clearly no time to speak about nonlinear algorithms here, but we also have results for that. So linear algorithms are of this form. You take your information mappings and the algorithm computes all these n informations and build them together in a linear manner, right? So every algorithm is specified by information mappings and reconstruction functions, or whatever it is. And what we want to bound is the worst case error. So as I said, we have some class f, and we want to know what is the worst case error that the algorithm is doing, measured in an L2 sense. We are doing L2 approximation. Okay? And this is called the worst case error of the class, of the algorithm an over the class f. Clearly, to say it here, several other settings are possible. So you could think of LP approximation, you could think of other measures, not the worst case, you could take an average case or probabilistic settings. There are many settings here. I am considering the worst case error. So we really want an error guarantee. We want that the algorithm we use have a guarantee to make a small error if we can bound this one. Okay, and since we don't want to consider one specific algorithm, we are more on the theoretical side of the world. We want to take the best algorithm given some information. Right? So, and these are the quantities I want to compare here. First is the sampling numbers, or to be precise, the linear sampling numbers. It's the minimal error, minimal worst case error, that can be achieved with n function values. You see, the information is given by function values. I'm taking the infimum for the worst case error, and then I take the infimum over all sampling points and over all reconstruction functions here. And as a benchmark, so if you want to know how small this quantity can be, you should take a benchmark, right? You need something to know what do you mean by small. And in this case, we take the approximation numbers, or linear width, usually called, an of f. And it's the same object as here. Now we really allow arbitrary linear information. Okay? So this is really the best you can do if you restrict linear algorithms. Okay? As I said, for some classes f, there's really a restriction. Sometimes linear algorithms are not so good, but at least the comparison of these two quantities makes perfect sense. And the point is, so clearly the approximation numbers are well known and well studied. There are many examples, many theoretical results. I will come to that in a second, I guess. But the GNs are much harder to analyze. Right? It's something depending on the specific space and careful analysis and many indices and spaces with 3 indices and boundary conditions. And then you can do something, right? But you always have this major restrictions on everything to prove bounds on the sampling numbers often. But clearly what we have is the approximation numbers, so that's the effect, the approximation numbers are smaller than the sampling numbers if this is a continuous linear functional. And now what you want to ask is there a bound that compares these two also in the other direction? Right? So how large can the difference be between sampling numbers and the approximation numbers? And the earlier results I don't talk about specific classes. All the results I'm presenting are basically all for all classes, or at least for a large class of spaces. And so these are the only known results that were known in these cases before I and David Krieg basically improved this result, second one. So the early results are as follows. If the approximation numbers have a certain decay, let me start with the second one. If they have a certain decay, if the approximation numbers decay like n to the minus alpha for some alpha larger than 1/2, then one can prove that, at least if the class is a Hilbert space, the sampling numbers also decay. It's completely non-trivial, right? To check that the sampling numbers really have some order of convergence, the approximation numbers have an order of convergence, this is a very deep result. Okay? But the thing is, you see, you only get half of the order of convergence. And you need this alpha larger than 1/2. Okay? So what the next step basically was, I think the result is older than this one, although the years are different. If you have a sequence that is not in L2, so if the decay of the approximation numbers is not large enough, then there exists a space such that the approximation numbers are like these ANs, right? But sampling numbers decay arbitrarily slowly. Okay? Here's the double log. So that's basically useless. So function values are useless, although approximation numbers have a decay like 1/√n, right? So the sequence AN equals 1/√n is a sequence that's not in L2, right? It's close to that, it's not in L2. So then you already find a space where it is not possible. Okay, the general result I then proved together with David in a row of papers, with intermediate papers of other guys. There are as other inputs, and I will come to that in a second. That's basically a very positive result, and very positive in the following sense. We now know that the polynomial order of convergence of sampling numbers and approximation numbers is the same in this regime here. So in the regime where sequence is in L2. Okay, so let me tell you what it is. So if F is a separable metric space of functions such that point evaluation is continuous, these are technical restrictions that are actually always fulfilled in all the cases we are interested in. Then for every p between 0 and 2, there is a constant such that the sampling numbers can be bounded from above by some log n and these LP sum here. Right? So what does it mean? It means if the approximation numbers are p summable for some p smaller than 2, then this guy here is finite, so it can be applied, and we will see in a second what it means for specific sequences. It's a rather tight bound here. And let me add, if this is a unit ball of a Hilbert space function, then one can also prove that the same result holds with p equals to 2. Okay, but I can do that. So in particular, that's the corollary here. If f is such that the approximation numbers decay like n to the minus alpha times log to the beta, for some alpha, then we obtain that the sampling numbers are bounded by n to the minus alpha times log to the power beta plus 1/2. We only lose log 1/2 here for the sampling numbers. Stated a little bit differently, if you have a problem and you know that 1/epsilon to the power q, some q smaller 2, arbitrary informations are enough for an approximation with our epsilon, then you immediately know that the square root log 1/epsilon divided by epsilon to the q function values can do the same approximation. And note that basically we don't really have a restriction on the space except its decay on the approximation numbers. Right? So that's really a kind of fundamental result because we don't need to take specific examples. But clearly examples are interesting. So let me show you one of my favorite examples, which is related to discrepancy and so on. So you know that. So we take Sobolev spaces with mixed smoothness, and we just define them in the usual way. We take the torus, we take as a measure, we take the Lebesgue measure, we take some p between 1 and infinity, smoothness now a natural number. It was not so important for this definition, it is. And now we take the class WSP of all LP functions such that this norm here is smaller than 1. So it's the unit ball in the Sobolev space. And here all derivatives up to mixed order S come into play, and you take the LP norms. So the class W1P is the one that's very much related to discrepancy. Okay, so what was known for these spaces? First, what was known, as I said, this is now an example. We don't, in our general theorem, one might expect, right, that this is not, because it's so general, it's maybe off in examples that we know very well. And basically it was not. And this was a surprise at the time we proved this result. So if you take P smaller than 2 here, then it's known for quite some time that sampling and approximation are of the same order. And now if you take P larger than 2, and what's also known for very long is that the approximation numbers, so the best approximation you can do in these spaces, k is like n to the minus s, and then you have some logarithm to the power s times d minus 1. Okay? Approximation is done by frequencies in an hyperbolic cross, and so on. So to prove this is somehow like the proof of Roth for the lower bound on discrepancy, right? That's basically uses exactly this same technique you can do for every s. And as I told you, the sampling numbers are larger, so you also know this is a lower bound for the sampling numbers. But for P larger than 2, we only had this upper bound for quite some time. And this upper bound is here, you see the binomial order is correct. And here you have a logarithm s plus 1/2 times d minus 1. So it's like the s times d minus 1 here times an additional square root of log d minus 1. So an additional log to the d minus 1 over 2. The reason to believe that this was sharp, it was conjectured for some time. The reason to believe that this is sharp is closely related to the discrepancy problem, because one thought that if you get this additional log to the d minus 1 over 2 already for integration somehow, then maybe this is related to approximation 2. So it would not be a surprise if this additional 1/2 here must be there, right? And these upper bounds are achieved by sparse grids. And it was somehow, as I said, conjectured that these bounds were sharp. Basically, this was disproved 2 years ago with David Krieg. We proved some bound that's not final one. I showed you on the next slide. But we showed, and now we know that so here must be a gn, not an en. So this en is exactly the gn here. So now we know the sampling numbers are basically bounded the approximation numbers times an additional plus 1/2, right? Which is better for all s larger than 1/2 and so on, and for all d. So basically we beat sparse grids. We know that sparse grids are not optimal. Okay, where's the drawback? The drawback is it's only an existence result. So that's really there deep. The solution of the Decades-Singer problem is involved, and so there is only an existence result on the points. But what I think is an interesting point here is if we take a little bit weaker bound, then we can just use IID random points. And additionally, we know it to some extent explicit algorithm to do so, right? So what is the result then? I'll present it in a second. Let me first comment on the explicit algorithm. So what is a classical way based on function values to find approximation? Right? To find an approximation, most people use least squares methods, right? It's not only old and classical, it's also powerful, so many people use it. So you just take some weights, some subspace Vn, and some points xi, and then you compute minimal g, so the g that minimizes this discrete error here. Okay, that's the algorithm, and it's known that this is a linear algorithm and can be represented by matrices and so on. I will come to that in a second. And then what then comes out is if you start to do that, and basically in every paper you look on these least squares methods, if you look for a worst case error analysis, or even in the probabilistic setting, you will see on stage 2 or 3, because that's what's happened after the first 2 calculations, that everything depends on these quantities here. And that's not hard to imagine, right? What are these quantities? This one is called the Christoffel function. Okay, maybe it's not completely easy to see, but this is some kind of the infinity upper bound, the norm on the L infinity norm of all functions in Vn. It's also not hard. Right? This is one quantity that appears called the Christoffel function, or the inverse of it, and the other one, the approximation error, the best approximation. So also that this quantity appears is not quite special or not quite surprising. And so the idea of David and myself was to just include both quantities into our approximation method, right? Into our density, which makes it non-constructive because you don't know this density, but we were interested in a theoretical result. Okay, so we wanted to compare Gn and An, and for this we consider here the weighted least squares algorithm. Here's just the function volume difference, and here's some function rho, right? And this rho is given here. It now depends on such functions bk here, and I'm only saying bk is what we define as a good basis of f. Let me say that bk is in general not known. It's just an existence result. I most likely don't have the time to tell you what I mean by that, but just say that for every f there exists such a good basis bk, and we define the density based on this sequence of bases. Yeah, and there are some sequences wk. As I said, everything is not quite constructive here, but we can at least write it down. And what do? We now choose the points xi just with this mu density. So with the mu density rho, and then sample x1 up to x big N IID with respect to this density. The outcome, and this is really the most general result, I guess this is not, for several reasons, just not improvable, so to say. But let me first say what it is. So if you take an arbitrary countable set, a subset of L2, and take n big N IID points, where n is larger than n log n, so you need some oversampling, then you get the same bound I've mentioned to you without any logarithmic factor. Okay. So this shows that if I take a logarithmic oversampling, I take log n times log n points instead of n optimal informations, then I get precisely the same, right? Without losing anything. Which means if you take log n oversampling of points, yeah, you can forget about optimal information, at least if you can in general approximate functions in your class well. Yeah, the countability is just a measurability assumption. Okay, let us come back to this example, and this was the first result we had here, David and myself. So what we get out of the first result we had here is first the good orthonormal basis is given in this basis by the trigonometric system. This is well known, and by this we also know that we can choose the density constant 1 in the example I just showed you. So the result here then shows that if you take n independent and uniformly distributed points in the cube and use them with least squares for approximation, then you are basically as good as using n divided by log n optimal informations, right? Which already gives this here and is at the end better than the sparse grid algorithm. Okay, so here's the picture just for you to have, for those who don't know that. Here is the bound we had. Let me show it again. That's the bound we had for sparse grids, right? And this is now improved by the result is here. And this is a sparse grid. That's the point set that's usually used for approximation, and everyone thought this is an optimal point set. Okay. Now we just use a random point set where even big holes are in it and stuff like that, and still we are better than these point sets, and still an open problem what optimal points are in this case. Okay, so far we only discussed random points and so on and so forth. and how you can approximate with them, but there were no random matrices involved. So let me tell you where the random matrices came into play. And since the proof is to some extent easy and has some important steps in it, I think it's a good idea to present it here. Okay. So if you don't can follow me in small parts because of a technical slide, that's not a problem. The proof now is somehow divided into 5 small parts, and if you don't get one, there is no problem. You still can check the paper if you want to. Okay, so what is the first important insight that you need? You need, and that's something you learn in the Numerics 1 course, that a least squares algorithm can be written with the help of a Moore-Penrose inverse of a matrix. In this specific case here, that's where you need some computations, clearly, but just believe me, you can write the algorithm I have by this sum. Okay? And here, as I said, NF is now the weighted information mapping. Here are the function values in it. It's the information I'm computing. I scale that by my density for technical reasons. G plus is the Moore-Penrose inverse of this matrix. You see, there's our basis involved, and again, there's the density involved. Okay, so that's the first insight one should have. And if I now want to check what is the error of this algorithm, right? What is the L2 error here of the approximation? You just use basic triangle inequality. This step, you use that the algorithm is exact on the space Vn. Oh, wait, maybe I haven't said that. It's obvious from the definition. If f itself is a function from Vn, then you can find the function such that this guy here is just 0, and this is the function f itself, right? So this guy is exact, outputs f, if f is from the space, from the span here of the first n good functions. Okay, so triangle inequality. The first part here is just f minus the projection on the first n, right, which is the optimal algorithm. And so this is smaller than approximation numbers. And the second part is just, as I said, I use matrix representation. And here is f minus p and f in it. Okay, and now the main task is to bound this. And it's not very hard to see. It's a little bit technical, because there are several sums involved, infinite sums, and you need to guarantee that you can interchange summation and stuff like that, right? So for this, we need the countability and some of these assumptions that we post. But yeah, it's just, you can write it like this. This is just everything matrices, so to say. So you can just bound it by the matrix norm of G plus of the Moore-Penrose inverse and norm of this guy. That's the L2 norm, the finite L2 norm here of the information mapping. Okay, so overall, the worst case error of our algorithm in the class F0 can be bounded by this quantity, which is same as the smallest singular value of G. The operator norm of the Moore-Penrose inverse is the smallest, is the inverse of the smallest singular value of G. And this guy is still here. Okay? Take the sup over all f and this. Okay, so what is the rest of the proof? The rest of the proof, now we know this formula here is basically control the smallest singular value and this guy. Both of these guys are based on the random point sets, right? And both are matrices, as you will see in a second, can be represented as matrices. And so what you have to do is you have to control the norms or all singular values of random matrices. And we will prove our result once we show the following two facts. And the facts are, if we take the big N of the order n log n, and simultaneously and with high probability, the smallest singular value of G is bigger than this big N, so the number of points. And this guy here is smaller than n log n, like the quantity we are interested in, okay? To the power 2. Okay, we take squares here because it's nicer, whatever. Okay, so we want to prove these two facts simultaneously with high probability. And once we have that, You see n is approximately n log n, and if I just insert these two inequalities in our upper bound, we see that we are done then, because the big N and the n log n cancel out each other. Okay, how to prove these guys? And that's, I think, an interesting fact, and was also the fact why we were so surprised of our result, and maybe others also, is that the proof is so basic. We only use a very basic inequality here on the norm of random matrices, of random rank 1 matrices. And that's a well-known result. I think everyone will know this result, and it will be in a probability theory lecture. Most likely it's present from now on, because that's just the final answer to a very long problem. Okay, so what is the answer with the question you don't know? If x is a random vector with complex entries, say here in CK, here's some k, right? And the L2 norm is bounded by some r with probability 1. Then you take independent copies of these guys, right? Build the rank 1 matrix out of them, so just multiply x1 by x1 transpose, or complex conjugate. Then this is a rank 1 matrix, and what you get out of this result is that probability, the difference of the sum of rank 1 matrix and n times the expectation of this rank 1 matrix, so the probability that this is large is small. Okay? And this formula is easy. Every constant is explicit. And the only thing you need to control is the L2 norm of the random vector. Right? It cannot be easier. There's basically nothing to prove here. If you are in many examples, that's very easy to apply and surprisingly sharp. Okay? And interesting thing here is the whole bound is dimension free. Right? It holds in the same way if you set k to infinity. There is no problem at all in considering sequences instead of vectors. And that makes this result so powerful. Okay, and we now want to apply it twice. First, remember that's the good basis. We consider the vector xi, which is just given by these vectors, scaled by rho. Right? Xi depends on the point xi, and xi is chosen with respect to rho. Okay. Why do we choose this vector? We choose this because then the sum of the rank 1 matrices we get out of that is just the same as our matrix G we are interested in, but here we take G transpose times G. Okay. This is this matrix. Okay. Now it's easy to check. That's an orthonormal basis. The expectation of this matrix is just the diagonal matrix, the operator norm, so L2 norm is 1. And what we also get is there's the norm of this xi. Just check, that's directly written here. So the L2 norm squared is 1 divided by the density times the squared sum of these vectors. Okay. And this was the reason for choosing our density as it is. Right? Let me come back. Our density is complicated and has 2 parts. The first part is this finite sum. The second part is something else, but this is the first part. And here you see why we choose this part. Because now we know our density is larger than the sum divided by 2n. So this norm is smaller than 2n, and this 2n is our r. Plugging this into the inequality we want, we get the operator norm of this difference is larger than n over 2, so is smaller with is smaller than 1 over 2 with high probability, because the probability that it is large is small. Okay. And for this we need to choose n equals n log n and t equals 1/2 in the proposition above. Okay. And from that we get the smallest singular value of g, which is the small squared is the same like the smallest singular value as g transpose g. And this can clearly be lower bounded. That's kind of a triangle inequality using the Rayleigh coefficient for defining the singular values. You get the smallest singular value of this guy is lower bounded by the smallest singular value of n times e minus the norm of the difference. And since smallest singular value of n times identity matrix is n, and this guy is smaller than n half with high probability, we get the smallest singular value of g. It's large with high probability. Okay? This is the first part, and basically all we have to do for the for the part G. That's the approximation part. I haven't said what they are representing. So let me now go to the second, and that's a bit technical, and I don't want to go too detailed over all that. But I think this is an important step in the proof because it somehow shows how results on Hilbert spaces can be transferred to arbitrary spaces. And yeah, for those who are interested in, you can find that in the paper. But let me just tell you how we managed to deal with this problem. If you see here L2 norm of something, right? Then you might be tempted using, okay, there's an isometry and so on. So to get L2 norm of f minus p and f, right, somehow as an upper bound, right? Just get the norm of n somehow, and then an upper bound on f minus p and f measured in an L2 norm. And this would be optimal. And this is a good idea and so on. But this direct idea only works if class you're considering is a Hilbert space. Right? It's just because this isometry does not work if you don't have an orthonormal basis in your class of functions you want to approximate. Basically, our class F is not even a vector space. So this does not work, but that's only the technical reason. So what we did is, instead of taking the infinite rest that is there, this f minus p and f, split everything up in blocks. Okay? So we find some blocks depending on this n and l. These are submatrices of an infinite matrix of order n. N is the number of samples, xi, times n to the 2l. Not so important what's written here. And what we are then doing is we think that this guy can be written as kind of a matrix, including these matrices I've just defined, and the Fourier coefficients of f here. And here's a big question mark above. I think I won't have time to discuss why this equality holds, but yeah, as I said, just believe me, it's not a hard fact, but you need some restrictions on functions f. This can now be upper bounded because everything is matrices here. Can be upper bounded just using triangle inequality, and for each of the individual guys, you just bound by the operator norm of this matrix, which is a finite matrix now here, and small L2 norm of these Fourier coefficients. Okay, and now we know these guys here, some of the Fourier coefficients is bounded by the approximation numbers. It's also something you need to believe me. That's something I would have discussed in the part that I've deleted. But some of the Fourier coefficients are bounded by the approximation numbers. Let me write that just on a. Let me come to that at the end, and then I can make on my camera and so on. It's easier. Okay, so at least this L2 sums here are always smaller than the approximation numbers. Because the approximation numbers is given by the L2 sum of all Fourier coefficients, starting with the nth one. Okay, that's the definition of the, or what means the definition, that's how you can define approximation numbers, at least in Hilbert spaces, and here similar holds. Okay, and the only thing that's missing is to bound the norms of these matrices here. Okay, let's do exactly the same trick again as we have already done. For fixed L, we now take again this vector, but now with coefficients in this XL here. Check what this matrix is, which is just the sum of rank 1 matrices. It's again gamma L transpose times gamma L. Looks exactly the same. That's all copy and paste here. You take the same expectation matrix. You get that the norm is equal to 1. Now you want to bound the L2 norm. You get again this quantity. Realize why we defined our density like it is, right? Just we define the density, we have a lower bound of this form, right? So you get also here that L2 norm of these vectors xi is bounded from above by some quantity here. What this quantity depends on n and L, whatever, right? So what we get, that's what I cannot explain in detail, some strange calculations here. What we get at the end is that the probability that this norm is larger than some n log n, the constant depending on L, this probability is smaller than something small, and it gets even smaller with 1 over L. With L, sorry. And this BL must be large. It's not important. So if you now just take a union bound, this was the reason making all these blocks small. If you now take a union bound, you get probability that for any L, this norm is large. This is still smaller than 1 over n, right? So we just proved that all these infinitely many block matrices have small operator norm with high probability. And that's something, and we just get that by some scaling with this L and making blocks out of it, right? And here, and in all blocks we can use, so to say, Hilbert space techniques. This was. Okay, so what we get, our bound is here the small L2 norm of this n is upper bounded some sum. Here we do some technical stuff, and basically this finishes the proof. Okay. Yeah, maybe I skip these two parts with the countable set. Let me give you some comparison again. Maybe I give you the result, and yeah. So what is the result we just proved? We proved that if we take n samples, which are of the order n log n, then we can reach almost the optimal error, right? But we don't want to take n log n samples. We only want to take small n of them, because we want to have the optimal order of convergence, and so on and so on. We don't want oversampling. And the good result here, which I think everyone, in addition to this result on random matrices, everyone should know this result. Everyone who works with sampling, with numerics, with every one of you should know that. And and the reason is just simple. It is the final solution, or depends on the final solution of the Cadison-Singer problem, which was open for 80 years, one of the biggest problems in mathematical physics and so on, right? And it turns out in the recent papers, where also I was involved a little bit, that this enables you to make a really nice downsampling strategy. It's not an existence, it's only an existence result, and it's not easy to do it on a computer or whatever. But if you are interested in the existence of good point sets, say on the sphere or so, and you know that you can do good things with n log n oversampling, then this result is probably a good source of finding how to avoid the oversampling, right? How to downsample. So what is the finishing of our proof? And this has a major impact on numerical analysis, this result here. To finish the proof, we take n good points out of n log n random points. Okay? So that's what we want to do. And how can you do that? And you do that with a result that is so nice that it's basically unbelievable if you think a little bit about it. You would think this result must be false. Try yourself to convince you, right? But there exists universal constants such that for arbitrary vectors, big N vectors in Cn, the only requirement you need is that each of the vectors has a small norm, right? If you take the square root, it must all be smaller than square root of 2 times n. Okay? That's all you need. Big N vectors, norm bounded by small n, right? These vectors are in small n. So the number of the norm is bounded by the square root of the dimension. Okay? That's all you need. If you additionally have that the vectors are good enough to be a frame, not a tight frame, but a frame, which means you take the average of these inner product here of the y's with the n, and this is good to approximate the L2 norm of W. If you know that, and n, big N, could be arbitrarily large, right? Then can prove that there must exist a subset of cardinality n, small n, such that the same holds. Right? That's something amazing. That's so amazingly beautiful. Sorry that I have to say that, but that's something. Yeah, I have seen so many applications right now where it just gives a beautiful answer to many of these downsampling questions and so on and so forth. So that's really something I guess you should know, and you will apply it at some point most likely. Yeah, as I said, so where is this version from? Just for you to get these abbreviations, I haven't said that. So that's based on the famous solution of the Cadison-Singer problem, which was solved by Markus Spielmann and Srivastava in 2015. And this solution was only a splitting into two blocks of these matrices. That's not completely what's written here, but this is the basis. Shortly afterwards, Nitzan, Olivieski, and Ulanovsky proved exactly this version here, without explicit constants. And if you want explicit constants, there is a new paper of Nitzan, that's Nagel, Schäfer, and Tino Ullrich. There's something in the chat. Should small m be big N? Where is? Oh, yes. I'm sorry. Yes. So this small m, this is the number of samples. That's the big N here. Sorry for the confusion. Right. Again, something. Only thanks I could have. Okay. Yeah. So this is the one, and Weaver is written here because Weaver was the one who was asking for this question here. It was Weaver's conjecture, and he showed that this is equivalent to the Cadison-Singer problem, which is very important in mathematical physics. And so this solution, it cannot be overstated how important this result is and will be, just for those of you who didn't know that. I have this version with explicit constants, C1, C2, and C3, and so on. We find in Nagel, Schäfer, and Tino Ullrich, not related. They show the result with explicit constants. Okay. Yeah, using this downsampling, we finally get what we want. Okay. It's exactly the result we had here, but you see, we don't have an oversampling anymore. For this, we need an additional square root of log n. And yeah, I don't have the time here to discuss why this is, where this log n comes from and so on. You are clearly invited to check my paper. And to give something I think is maybe interesting for your community. That's the reason why I want to mention that shortly. Okay, I was discussing now the talk and the proof and everything for function values. And one might ask, yeah, why function values? I'm talking about general function classes and so on and so forth. And the thing is, there is nothing special about function values here in this thing I've said. Basically, what the heuristic is that one should have in mind is, if the approximation numbers are square summable, then good information, whatever you mean by good, but good information is nothing rare. Basically, every information is fine. Right? But what we also know is, if the approximation numbers are not square summable, then arbitrary information might be completely useless. And let me state just the result to see what the structural properties of our information is. So what we are now interested in is minimal worst case error that can be done by linear algorithms based on optimal information, from the class lambda. And lambda is a given class of admissible information, might be function values or coefficients of something. And this is a work in progress. It basically follows directly, but you need some functional analysis stuff. That's not that ugly. What we prove is that for the same classes above, just take a countable set or just take an arbitrary separable metric space. If you have a subclass of linear functionals, such that there exists a measure on this class such that it can reproduce the inner product for all f and g, then you get exactly the same result for function values. And just to see how this implies, if you just think L of f is f of x, so LF is a function value, then this is just definition. really nothing happened here. That's exactly what we had. But you might also think on other classes of information. For example, take an arbitrary orthonormal basis, take your favorite one, the Haar system, or whatever you want, and our result shows that every orthonormal basis satisfies this. You just take the counting measure, and you see that this integral is just the sum, which is, since hi is an orthonormal basis, just inner product, right? So in this formulation, f does not appear at all. You don't have any restriction on this guy here, right? And this means if your approximation numbers are square summable, then actually every L2 basis that you have produces nearly optimal information for L2 approximation. And that's, I think, a rather beautiful insight, right? It's not that your space can be so difficult. Think on the sphere. Optimal L2 basis for approximation is a difficult object. But you could also think of completely different, much easier wavelets or whatever. And this result shows that wavelet coefficients do the job, basically. Okay, yeah, again, algorithm is just least squares based on the given information. Yeah, C is no information. And the density is again like that. And so nothing new happens here. Okay, yeah, so what are the open problems and the final remarks of my talk? First of all, is this log n factor needed? Unfortunately, I haven't talked that much about this part, so it's hard for you to guess why it could be there and why not. But the last two are most likely interesting for you. I just told you that sparse grids are definitely not optimal. And we know from this stuff here that random points do the job, right? Take n log n points and they are better than sparse grids. And even more, n log n points contain n points, which are very good, right? And the question is, what is an explicit construction of such a point set? Really, for these classes of mixed smoothness, this is a very challenging and will most likely be a long-standing open problem. If you have any ideas of such constructions that are not lattices and not nets, for nets it will also not work. I think it's not proven it will not work for nets. I'm very, very sure. What could be, that's also a question to you, maybe some of you have an idea, what would be a candidate of any point construction that is not a lattice, that is not a net, and that is not a sparse grid? Because these are all constructions I know, and all these constructions are proven to be not good enough for L2 approximation. Or at least to know what are necessary and sufficient conditions of a point set. So the only necessary conditions I know is don't put all of them to 0. Basically, that's the only one. Because if you take a very smooth class of functions, analytic functions, then you basically can put all points very close to 0, and you can produce a good approximation, because for an analytic function, you can just compute all the derivatives, approximate all derivatives, and then you take the Taylor polynomial or something, right? So for me, it's not clear what a good point set could be and how to define necessary and sufficient conditions for that. Okay. And this shows, by the way, we still don't know enough about some of the easiest approximation problems in high dimensions. Okay. Just consider the class W1D. Okay, that's the class of functions you study when you are study star discrepancy. Right? Integration of, so the star discrepancy is related to numerical integration in the Sobolev space W1D. Right? So yeah. Smoothness 1, P also equals 1. Sorry, that's the point. And that's the class you are studying, right? And we still don't know how to approximate these functions in an L2 sense, in an optimal way. And that's kind of annoying stuff. So thank you very much. That's all I want to say. Sorry, I've took 5 minutes more than expected.
You're fine. So do we have any questions for the speaker?
Oh, I have a small question. You talked about, you have a lot of examples for the classes of, actually Sobolev classes for mixed derivatives, right? But do you know some similar results for the class of infinitely differentiable functions?
For what?
You showed a lot of results for classes, like Sobolev classes with mixed derivatives, but do you know some similar inequalities for, or similar results for the classes of infinitely differentiable functions?
You mean if the order of convergence is exponential?
Yes, something, or like...
Yeah, okay, that's a very good point. The reason for that is, check it, hopefully I wrote it correctly. I wrote it correctly. You see, main problem is with functions where the approximation numbers decay exponentially fast, is that this guy is of the correct order. That's everything fine, right? But you lose a constant in the exponent. Right? So which means we can prove here if the approximation numbers decay like e to the, so 2 to the minus n, then we can probably only prove that the sampling numbers decay like 1.5
but when, for example, they decay, like, for example, like exponent to the power minus square root of n.
Yeah, no, it depends.
It's like smaller as a geometric progression.
Yeah.
Because usually there is like a different orders they have such quantities.
Yes, but so what I can tell you is that you can rewrite stuff in saying that also in the exponential decaying setting and sub-exponential setting and so on. So if you use n function, if you need n function values for approximation numbers, you need a constant times n for the sampling numbers. That's what you can prove. So if you reverse everything and write it down as a with the information complexity and not with the errors here, then it's maybe easier to see. So as I said, this result here always holds, right? For actually everything where point evaluation is defined. You need separability, okay? But it really doesn't matter what decay of your guys is, as long as it is large enough, you get the same order for these guys. You must be careful if you think about tractability and d-dependence and so on, and things can get difficult. So you need to check what the sum brings you.
Yeah,
sorry?
Okay, thank you.
Yeah, basically the question would be if p equals 2 here, so just the L2 sum of the approximation numbers, if this could also be true, if this could be the final answer to the problem and so on. Yeah.
Actually, like this kind of form is quite standard form for the approximation characteristic in LP, like without the square root of log n. It's like quite good form, I would say.
You mean e to the minus square root of n? Or what?
No, I mean like this sum, the sum of p coefficients to the power 1 over p. It's like good result.
Yeah, the thing is, we would like to prove it also for the case p equals 2. And maybe, hopefully my microphone doesn't make any difficult stuff now. Wait a second. You can still hear me, right?
Yeah.
Okay, let me shortly switch. You can make me large, that's easier. Let me switch my camera. So, I just want to say that if we take a Hilbert space, right? If this is a unit ball of a Hilbert space, then we know that. Here's a big N, and here is the square root of log n, and here we really get the square root. Okay, so this is really what we get if this is a Hilbert space, and most likely this just does not hold for arbitrary spaces. The arguments for that are a bit strange. That's like the convergence of Fourier coefficient of the Fourier series and so on. There is something called the Rademacher-Menschow theorem and so on. There are many relations in this direction, which shows that this result most likely does not hold if you take arbitrary f. So you need something closer. And what we actually proved, but as I said, I want to stay a little bit simple and want to focus a bit on the proof, is we proved it with a log n, and here we get a square root. But no, how was it? Yes, it was a square root. And here's some log k. I think to the power 1 plus delta or something, right? And here are ak squared. So you have something like an L2 sum, but you need an additional logarithmic decay of the approximation numbers to, and so on, right? This is, I think this is basically what we actually proved, but you can then show that this guy here is just smaller than the LP norm if you make P smaller than 2, something like that.
Okay, thank you.
Other questions?
Hi. Yeah, I have a question.
Please.
Yeah, thanks a lot for the great talk. I was wondering if the in your papers you also discussed, because you discussed the example, your favorite example about Fourier, and in your papers do you also deal with orthogonal polynomials? And it's also related to Tatiana's question, especially for me. Okay, I'm biased by my research, but like approximating, for example, holomorphic functions with orthogonal polynomials in high dimensions. So is this
the question is, what would be the goal? Maybe I don't get completely what the goal is. You want to approximate this function by function values, like in the setting, right?
Yeah, approximating a holomorphic function on a, let's say, hypercube in the dimension, and then you use orthogonal polynomials. So maybe Legendre polynomials or Chebyshev polynomials.
Okay, the point is, so this is your f, right? It's just any f. Do you know how the approximation numbers decay of this guy? Do you know that?
Yeah, so I think it's known. So I don't. Yeah, I'm not sure right away.
But you think something like e to the minus n, or what is the point, or square root of n?
Yeah. Or like n over d in dimension d, I guess. Something like that.
Yeah, okay. N over d, something like this. Whatever. So, yeah, you could, for your example, you can just put it in, right? Just compute what the sum is. So I think that's geometric. Yeah. So if you put it in, it's basically a geometric sum, right?
Yeah.
So there is nothing. I could do it now, but I don't think that we will learn a lot if I'm computing a geometric sum.
Already kind of worked out, but no, I mean, I'm not asking you to work this out right now.
No, yeah, it's really, as I said, just a geometric sum.
Yeah, it's plugging in, yeah.
There is a work of Henryk Wozniakowski, David Krieg, and myself. It's in preparation because Henryk is a bit ill at the moment. And there we explicitly make tractability for exponential convergence.
Okay.
So, and basically we settled all open problems that were open still. If this is so, also in a general setting. So if you know that if you have exponential convergence, let me think, right? That's, and just share the paper. Come on, what else? Where is it? Random info? No. Leave squares? No. Yes, at some point it is. Here. It's really completely work in progress. So I think we will need half a year or so to make it at some point if you want to have it. So this is our result again, and what we then proved is basically this result. Okay, and it shows that if number of function values you need for arbitrary linear information, and in the example you showed, this means something like linear in D, but logarithmic in 1 over epsilon, right? So this shows that the number n all is something around D times ln of 1 over epsilon, right? Because that's how it is. You could now play with the powers, but that's what it is. And if we know that the number of function values for lambda all of this form, then we get that the number for function values we need is basically same. Oh, I think. A second, something is missing here. Yeah, somehow you need to take the second one. Sorry, the first
So
one
this,
is our.
this is a preprint. So this is.
Yeah. That is so preprint. The first equation here is just my conjecture. So this will not stay in the paper. So this is what we now prove at the moment. And what we prove is if you can do with arbitrary information with d to the q and log 1 over epsilon to the p, then you can do the same with d to the q and then some additional log d to the p power here. Ah, no, there is it. There's the d. It's correct. I'm sorry. I lost the d here. But yeah, that's also correct. As it will. So does this answer your question, or is it?
You know, I mean, it was not a precise question. I was just curious if you kind of worked on this type of examples.
Yeah. So
Okay.
it depends what you mean with examples. In our case, it's so the only restriction we want to pose is any decay of the error that you can do with arbitrary information. And under this, and if this is our only restriction, then this is what we can get. And it's amazing. In many cases, like also here, we basically get almost the optimal result. So almost the optimal dependence on n, all these quantities, although we assume nothing about f, except that it has some decay, right? And I think that's interesting point here. But the thing is, it's only an existence result, and as I said, the result is as powerful. I probably say, and it somehow sounds a bit unbelievable. It also sounded unbelievable to me, but it is based on this heavy result of Cadis and Singer, right? That's such a very deep result in it that once you know the proof, you realize, okay, it might be true. That's kind of strange.
Okay.
Yeah. So. Yeah, but you are right, and the question was good with the exponential convergence, because then constants play a role, right? It really depends what you mean by optimal, because some people, let me switch here again, would not want to know that the basis here is the same, right? So if you know that an is of the order, say 2 to the minus n, they would not be satisfied with a relation like whatever. No, what is it? Yeah, something like this. Right? Because they want the right basis and so on. So this is something we don't get at the moment, right? Because we always need to have an additional constant in front of the n. So we don't get, and this is not possible, by the way, to find n function values that are as good as n optimal informations. It's in general just not possible.
Any other questions for the speaker? All right. Well, then, if not, let's thank the speaker again.
It was a pleasure.
Thank you for the great talk, Mario. And yeah, thank you for the flexibility of moving the time around a little bit. I'm sorry about that, but we really appreciate it.
No problem. No problem. Yeah, this was somewhat strange with the talk because it was, yeah, Albert took his time, and so, but I wanted to hear the end of the talk because, yeah, it was crazy. That is anyhow a crazy week.
Yeah.
And maybe you could stop recording, right?
Oh, I forgot that I was still recording.
I do interrupt.